Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 19 on this NPTEL course on fluid mechanics for chemical engineering undergraduate students. In the last few lectures, our topic of discussion was the derivation and application of integral or macroscopic energy balance. And just to quickly remind you, the macroscopic energy balance is derived using the first law of thermodynamics. The first law of thermodynamics applies to a system which contains a particular mass of fluid, while in many engineering flow applications we deal with flowing systems. So, therefore, we have to convert the first law of thermodynamics to a control volume, which is basically a fixed region of space of interest to us in an engineering operation. So, we had to use the Reynolds transport theorem to convert the rate form of the first law of thermodynamics, which simply says that dE dt for a system is rate at which heat is transferred minus to the system minus rate at which work is done by the system. Just to reiterate again, the work transfer between the system and surroundings involves a sign convention, and we are going to follow the sign convention that the work done by the system or the CV on the surroundings is positive, while the work done on the system or the CV is negative. So, that is why you see a negative sign in this expression for first law of thermodynamics, while if you use the other convention that work done on the system is positive, then you will have a plus sign. Okay. So, that is a sign convention that can also be adopted, but we are going to follow this sign convention, which is typical in many engineering contexts. Okay. So, then use the Reynolds transport theorem to convert this into a CV formulation, wherein you get rho E dV, where E is the total energy per unit mass and E is written as the internal energy plus unit mass plus the macroscopic potential energy plus unit mass plus the gravitational potential energy plus unit mass. This is the rate of change of the total energy present in the control volume, but this is not all. You also have the flux term over the control surface, rho E V dot N dA is is equal to the rate at which heat is transferred into the system minus rate at which work is done by the system. Now, there are various contributions to work. Okay. Suppose you have a control volume which looks like this. Okay. So, this is a system in which fluid is entering through a pipe and exiting through a pipe, let us say. Okay. So, now we are going to draw the control volume like this using the red dotted lines. Now, that is the red dotted line, therefore, becomes the control surface that demarcates whatever is inside, which is the control volume, from the surroundings. Now, fluid is entering like this here. So, the unit outward normal here is like this, while the unit outward normal is like this. The velocity vector is pointing against the unit outward normal at the inlet and along the unit outward normal at the outlet. Now, there are various types of work that are possible, but what is important for us to understand is that work is done only if there is a force that acts and there is motion in the line of action of the force. So, in this control surface, suppose you consider this internal areas where there is flow, where there is no flow because the fluid is stationary at the wall. Okay, that is called the no slip condition, which we will see in detail little later. Okay. So, although a stress acts on these internal surfaces, there is no work done on those surfaces because the surface itself is stationary. Okay. So, here there is a pressure force that acts, there is a normal force that acts, okay, and fluid is also flowing. So, therefore, there is a work contribution at the inlet and outlet that will be given by, we later saw it to be equal to the inlet and outlet. So, there are these normal contributions to the force that comes from the work done by the normal stresses at the inlet and outlet, which I will write shortly, and there are also shear contributions because of the fact that you can have shear work done by an impeller at the control surface. So, having included both these terms, we saw that the left side remains as such, rho E dV plus integral Cs rho E V dot N dA is Q dot. Now, this is denoted as a shaft work, okay. This that is associated with pumps, compressors, turbines and so on. So, either you could do work on the CV or the CV you can extract work out of the CV. Now, the term that arises due to the fact that you have a normal force due to pressure is given by rho integral P V dot N dA integral over the inlets and outlets, okay. And in general there is no shear work at the entrance and exit, because if you choose the control volume that is normal, if you choose the control surface to be normal to the inlet velocity, the shear stresses act in the direction perpendicular to the inlet velocity. So, the dot product of these two orthogonal vectors is obviously 0. So, the shear work can be set to 0 by choosing the control surface carefully. So, after having done all this, you therefore get, and then let us simplify, V dot N is minus V for inlets, is plus V for outlets. So, once you do this, you get a very simple dV is equal to Q dot minus W dot shaft minus integral rho times E plus P by rho plus V for inlets minus rho E plus P by rho V dA over outlets, because of this fact, okay, that V dot N is minus V, therefore minus of minus becomes plus here, whereas plus V for inlets, well, it is minus, it is just plus V for outlets. So, this minus sign stays here, okay. So, this is the integral energy balance. Now, we also said that we can simplify this further by making assumptions of, just for the sake of clarity, obtaining clarity, and okay. So, you can use the assumption of uniform flow. We of course saw that we can correct this assumption by using the kinetic energy correction factor for the energy balance, okay, the alpha term. But right now, if you assume uniform flow and steady flow and single inlet, single outlet, when the flow is steady, this becomes 0. When the flow is uniform, all these quantities are independent of the cross section. So, you can pull it outside the integral, same here, okay. So, the area integral becomes just the area of the inlet and outlet. So, having done that, you will get, okay, E plus P by rho times rho V A at the outlet is E plus P by rho V A at the inlet plus Q dot minus W dot shaft, okay. Now, the mass balance will say for a single steady system with single inlet and single outlet, that rho V A at inlet is the same as rho V A at outlet, because at steady state there is no accumulation of mass in the CV. So, that is equal to m dot, the mass flow rate. So, if we divide by m dot, we get E plus P by rho at the outlet is E plus P by rho at the inlet plus Q dot by m dot minus W dot shaft by m dot. Now, this is nothing but the amount of heat transferred to the CV per unit mass. There is no rate involved, because you are dividing one rate by another rate. So, they cancel out, and this is denoted as W shaft. There is no rate involved anymore, okay. So, now as per second law of thermodynamics, okay. So, once you expand E to be U plus half V squared plus GZ, you get change where delta means change in out minus n, u plus half v squared plus p by rho, let's write p by rho first, plus half v squared plus g z in minus, where delta of any quantity is that quantity evaluated at out minus in. Delta symbol implies that you are evaluating quantity at the outlet minus the quantity at the inlet. So, this is equal to q minus w shaft. If I want to use thermodynamics, I want to change it to a differential where the inlet and outlets are just separated by a small distance. So, you can convert it to a differential d of u plus p by rho plus half v squared plus g z is del q minus del w shaft. Now, you can now borrow or adopt a relation from thermodynamics. Du is T ds minus P dV. V is a specific volume which is 1 over density, is T ds minus P d of 1 over rho. When you substitute this back out here, then you get du instead of du. So, I am going to substitute this in the du here. So, instead of du I will get T ds minus P d 1 over rho, okay, but d of p over rho will give me d of p over rho will give me P d 1 over rho, okay, plus 1 over rho dp. Okay. So, I am going to write this as plus P d 1 over rho plus 1 over rho dp plus half dv squared plus g dz is del q minus del w shaft. Now, these two terms will cancel each other to give, and I am going to bring the del q to the left side to get T ds minus del q plus dp by rho plus half dv squared plus g dz is minus del w shaft. Second law of thermodynamics tells you that this term is always greater than or equal to 0. This is second law of thermodynamics. Therefore, and this is basically the amount of work that is lost irreversibility to heat, and this equality is valid only for a reversible process, but engineering applications involving flow or irreversible processes, you do not do them infinitesimally slowly over a sequence of equilibrium states. So, they are irreversible processes. Therefore, second law of thermodynamics tells us that this is greater than 0 for flow applications. This is the amount of heat, amount of energy that is lost as heat and ends up in increasing the internal energy of the fluid. This is also called as the viscous dissipation of energy. Viscous dissipation of energy. Now, from the point of view of fluid mechanics, this is the amount that is lost. So, these are termed as losses. Okay. So, this is written as WL, amount of energy or work that is lost. So, you rewrite your energy equation, simplified energy equation as P by rho plus half V squared plus GZ at outlet minus P by rho plus half V squared plus GZ at the inlet is minus W shaft minus W losses. These are the viscous, this is the viscous dissipation of energy, that is that implies that energy is transferred from macroscopic forms like work to internal energy. Okay. Now, how to compute these losses we will come to a little later when we do differential balances, but right now this you have to sort of know the losses if you want to find the pressure difference and so on. So, either the losses come as an input to the calculation through experimental data, or they come out as an output of the calculation. Okay. So, this is the energy balance after taking into account the losses. Now, after finishing this, we also looked at the application of integral energy balance to flow measurement, where we try to understand restriction flow meters, wherein essentially you had a configuration like this. You had a gradual contraction and an expansion. So, essentially fluid is flowing like this, eventually occupying the full region. So, there are recirculating zones, okay, like this on both sides. Okay. So, idea is here to have a knowledge. Suppose you take a streamline that goes from here point 1 to point 2. Okay. Now, if I measure the pressure difference between these 2 points, okay, there is a delta P. Okay. Can I relate it to the velocity at 1? Okay. That is the idea. So, you measure pressure difference between 2 points, one upstream of the contraction and another downstream of the contraction, and see whether you can relate the pressure to the velocity. We found that after making simplifying assumptions that there are no losses, and by applying the Bernoulli equation between point 1 and 2, remember that the Bernoulli equation is essentially gross simplification of the energy balance by taking the CV to be a stream tube, and by assuming that there is no viscosity in the surrounding fluid. So, there is no work done, and by shrinking the stream tube to a streamline, you find that P by rho plus half V squared plus Gz is a constant along a streamline. So, this is the Bernoulli equation. So, by applying this to these 2 points along this streamline, we found that we can say that P1 minus P2 is rho by 2 V2 squared minus V1 squared, and by using mass conservation we said that V1 A1 is V2 A2. Therefore, we were able to write this as V2 is 2 P1 minus P2 by rho 1 minus A2 squared by A1 squared whole to the power half. So, this was the theoretically expected V2. From here we can find the theoretically expected mass flow rate as rho V2 A2 is equal to A2 divided by root of 1 minus A2 squared by A1 squared square root of 2 rho P1 minus P2. So, what is the idea? The idea here is that by measuring this pressure difference between points 1 and 2, and by knowing the area A2 and A1, and by knowing the density, we can find the mass flow rate. Okay. But this is a theoretically estimated mass flow rate, but it has a lot of assumptions. So, in reality the observed mass flow rate will not be the same as this, because we have assumed that there are no losses, okay, which is a gross oversimplification. And another thing is that we do not know what is the flow area at point A2. At point 2 we do not know what is the area, because the flow area is only this, not the entire, because of the recirculation zone occupies a zone like this until the streamline occupies the entire cross section. So, this area is something that we do not know. So, usually what is done is to use the throat area. This region is called the throat, the area of the minimum cross section of the flow meter. Okay. So, instead of A2, now therefore, you write m dot observed, okay, or actual is AT. Instead of A2 you write AT, because that is something that we know from the construction of the device. AT squared by A1 squared root 2 rho P1 minus P2. but since there are so many approximations that are involved, there will be the actual mass flow rate will be some constant which has to be fitted experimentally or empirically by doing the following experiment. By knowing the given mass flow rate, okay, and by knowing the pressure, by measuring the pressure drop, we can fit the constant so that this equation is satisfied, and then this can be used to create calibration charts for a given meter. That is how the constant C changes, okay, as a function of flow velocity and so on. That will give us way to measure or way to compute mass flow rate, okay, in a real application by simply measuring the pressure difference at an upstream point of the flow meter and at the downstream point of the flow meter. So that is the idea of restriction flow meters. We also mentioned that this is just generic discussion, and in practice there are orifice meters and venturi meters which all fall into this restriction flow meter class of flow measuring devices. But one drawback of restriction flow meters is that you will be able to measure only the average velocity, cross section average velocity over the entire cross section of the pipe. But suppose for in some applications, if you need the local velocity at a given point in the cross section of the pipe, then what do we do? Okay, so this is where we left off in the last lecture. We just started this discussion on what are called pitot tubes. Okay. Now, one way to measure the pressure in a flowing liquid is the following. Suppose you have a pipe or a channel in which fluid is flowing, you can make a small hole, a pressure tab. This is called a pressure tab or a wall tab, and let us say fluid is flowing on the average in this direction. Then it turns out that there is no normal variation of pressure if the streamlines are straight, which we will see later. Okay. If the streamlines are parallel, then no normal variation in pressure. So we can just measure, okay, the pressure here by having a small tap and then connecting it to the manometer, which is exposed to the atmosphere. So you can measure the gauge pressure at this point of a flowing fluid by simply having a wall tap. So the gauge pressure in a flowing fluid can be measured by a pressure tap and a manometer. It is called also a wall tap. Okay. But that is not sufficient to calculate the local velocity at any point in the fluid. Okay. In order to do that, what we have to do is use what is called a static pressure probe. Essentially, what the static pressure probe is, it has, okay, a small tube, okay, and there are two holes, okay, at the top and bottom. Okay. So this one is another way of measuring the pressure in a flowing fluid. So the pressure that happens in the Bernoulli equation is also called, this is the Bernoulli equation, this is also called the static pressure. One way to measure the static pressure, that is the pressure in a flowing fluid, is to use a wall tap. Another way is to introduce the static pressure probe, which is a very thin tube shaped like this. Now fluid is flowing like this, okay, and this region will therefore feel the pressure of the flowing fluid, and if it is connected to a manometer, okay, then you will be able to measure, okay, the pressure that is present inside a flowing fluid, which is also called the static pressure, the key thing is to align this in the flow direction. This must be aligned in the flow direction. Okay. Now, another quantity of interest is called the stagnation pressure. Let me explain what this means. The stagnation pressure is that pressure, hypothetically suppose a fluid is flowing along a streamline, suppose you bring it to rest, okay, you decelerate it to a 0 velocity by a frictionless process. So, you decelerate a fluid to 0 velocity. This is a conceptual idea by a frictionless process. In reality, of course, it is not possible to in general to have a frictionless decay of deceleration of a fluid to 0 velocity. Therefore, but it is a conceptual idea, it is a concept that if you are able to decelerate a fluid to 0 velocity by a frictionless process, then what will happen is that if you take this streamline and apply Bernoulli equation between point 1 and 2, here the fluid is velocity of the fluid is 0. If the velocity is 0 here and it is V naught here, if you apply Bernoulli between point 1 and 2, Bernoulli equation between point 1 and 2, what will happen is that P1 by rho plus G1 Z plus V naught squared, which is the upstream. Let us call all these terms as let us not call this V naught, let us just call it V, let us just call the velocity in the fluid as V plus V squared is at the point, this is called a stagnation point where the fluid velocity is 0, this is called the stagnation point. At the point where the fluid velocity is 0, this becomes equal to, let us denote the subscript at this point as P0 plus G1 sorry GZ1 and similarly G Z0 plus V naught squared, but V naught squared is 0 because the fluid is static there, it has gone to 0 velocity. Now, if you assume that the elevations are the same, then these two terms cancel out. So, then that gives you an expression for V squared, this is not V2 squared, this simply let us call this V squared. So, V squared is P naught minus P1 by rho, or V since you have V squared by 2, you should have V squared by 2 here. So, V is 2 P naught minus P1 by rho whole to the half. So, this essentially says that the entire pressure head is there is on the upstream at point 1 there is a pressure head as well as the kinetic energy head. So, both the pressure head and the kinetic energy head are at the stagnation point are converted to just pressure, because the kinetic energy head is 0 there. So, that gives you an estimate for what is the velocity upstream. So, if you measure the pressure at a stagnation point, and if you measure the static pressure, which is the pressure in a flowing fluid, then that gives you the velocity at which you are measuring the static pressure. Suppose you are able to measure this pressure difference between a stagnation point and another point where the fluid is flowing, then you can estimate what is the local velocity of the fluid at that point where you have measured the static pressure. Now, how do we do this experimentally? So, this is conceptually how it comes about, but we also have to find a way out experimentally, and it is done by what is called the pitot tube. The pitot tube is a way to measure stagnation pressure. So, how it works is the following. So, you have a tiny tube, it is a small hole and which is aligned in the direction of flow, and the fluid comes to rest at this point approximately, and therefore, if you connect this to a manometer, you will get the stagnation pressure with respect to the gauge pressure, with respect to the atmospheric pressure, that is the gauge stagnation pressure. So, the pitot tube can measure stagnation pressure. the pitot tube can measure stagnation pressure. Okay. But there is also another variation, that is called the pitot static tube, which simplifies the two measurements in a single device, okay, which makes possible to measure both stagnation pressure and static pressure and the difference between them in a single device. This is called the pitot static tube, which goes like this, which looks like this. So, you have a tiny hole, okay, and there is the inner one, the inner tube, okay, is one tap which measures the stagnation pressure, because fluid is coming like this, and then there are holes which measure the static pressure. So, okay, let me erase this. So, let us show it with some other color. So, the inner tube this gives you the static pressure P, whereas the outer the tubes where the holes are on the surface gives a measure of the static pressure P, whereas this tube where the fluid comes to a halt, it gives a measure of the stagnation pressure P naught. If you connect these two ends to a manometer, this change in pressure, okay, will directly give you what is the local velocity using the formula we just derived, because we derived this formula, okay, which says that V is 2 square root of 2 P naught minus P divided by rho whole to the half. Since we know P naught minus P through the measurement by connecting a manometer between this inner tube and outer tube, then we can directly substitute that value out here, and you will get a measure of the local velocity. So, you can imagine placing the pitot static tube at various points in the cross section of a pipe or a channel, and you can therefore measure the local velocity at each and every point. Okay. As I have told you some time back, the velocity that of a fluid that flows within inside a tube or a channel varies at various points in the cross section of the channel, and that can be measured by using the pitot static tube, because it gives you a handle to measure the local fluid velocity. Okay. Now, this completes our discussion on flow measurement. So, and what I will do next is to apply the engineering balances, that is both that is all the three balances, mass, momentum and energy, to a couple of problems to illustrate the subtle points that come out upon applying these mass integral balances, because in general what happens while using integral balances is that we do not have all the data to completely solve a problem. Therefore, we are forced to make assumptions such as that there is no viscous shear stress existing on a wall when we use the momentum balance, for the simple reason that we do not know in a complex engineering situation what those forces are. So, we are forced to make the assumption that those forces are negligible, but then such assumptions may work in some contexts and they may not work in some other contexts. So, this is always an issue while applying while applying macroscopic or integral balances to engineering applications, because of lack of complete information to solve the integral balances. So, this I will try to show you in the context of two problems. Okay. First, let us imagine applying integral balances. So, imagine you have a sudden expansion of a flow. So, you have fluid flowing and you have one station, one upstream. So, let us draw the CV and another stream. Okay, let me draw it again. So, you have fluid flowing, there is a sudden expansion, you have station 1 upstream and station 2 downstream of the expansion. Okay, whenever you have an expansion, what happens is there are losses, because not all the energy that you put in by virtue of, let us say, pressure drop goes in pushing the fluid in the flow direction. There are recirculating zones which are just there because of the sudden expansion, which cause additional losses. Such losses are called expansion losses. So, let us say fluid is flowing with a given velocity, and we want to be able to find the amount of viscous losses that happen in a sudden expansion. So, we are now going to calculate the expansion losses, the viscous losses that occur in the energy balance. That is our aim when you have a sudden expansion. Now, the equations that we have are the three balances: mass, momentum and energy. So, we want to be able to find the losses, viscous losses due to the sudden expansion. So, using the three balances. Now, how are we going to do that? Now, if you want to use the energy balance to calculate the viscous losses, as I have told you, we need to know what is the pressure drop between point 1 and 2. If you want to know what is the pressure drop between point 1 and 2, then you have to use the momentum balance between these 2 points, between those two control surfaces, points in the control surface. You apply the momentum balance across these 2 points to estimate delta P. For that, we need to know what are the forces. Okay, so let me just draw this diagram once again. Okay, so as the fluid is flowing, there are two types of forces. One is the tangential force acting between point 1 and 2 on this surface. Okay, other is the normal force acting on this. Suppose you imagine this to be a pipe. Okay, this pipe is going like this, and it's suddenly expanding to a bigger pipe. So, there is an annular region, okay, where you have this normal force due to pressure. Okay. So, there are two types of forces that act on the surfaces of this CV. Okay. So, we have to keep that in mind. Now, let us first use the so let us use assumptions that we will use alpha 1 is alpha 2 is approximately 1, beta 1 is beta 2 is approximately 1. That is, essentially we are saying that let us assume that the flow is in the turbulent regime, okay, just to keep the flow to be reasonably uniform. So, you have A1 V1 is A2 V2. This is mass conservation for an incompressible fluid. This is equation number 1. The momentum balance tells you that at steady state 0 is rho A V1 squared minus rho A1 V1 squared rho A2 V2 squared plus P1 A1 minus P2 A2 minus F, where P1 A1 are the forces, P1 A1 and P2 A2 are the forces acting when the fluid is entering and leaving, okay, the control surface, and F has both the tangential and normal components. So, as I just told, this is the normal component due to pressure, these are the tangential components, okay, in the direction of flow. Okay. So, but we are going to say that the normal component is simply the pressure, okay, times A2 minus A1, because this is the annular area, remember, over which the pressure is acting, and the negative sign is because the force is acting in the direction opposite to the flow direction. So, you have to put a negative sign. Okay. So, that is one thing, that is a normal force. The shear stresses exerted by the fluid on the solid surfaces are very difficult to calculate or estimate, because we need a more detailed model such as a microscopic or differential momentum balance to get that information. So, due to the lack of that information, either from a more fundamental model or from experiments, we merely set it to 0 at this point. Okay. So, this is an assumption that we have to live with, because it's otherwise it's very difficult to find what the tangential forces are due to shear stresses. Okay. So, the momentum balance becomes rho A1 V1 squared minus rho A2 V2 squared plus P1 A1 minus P2 A2 minus P A2 minus A1. Okay. So, this is what we have at. So, now the point is this P is the pressure at the point where the sudden expansion occurs. So, let us call that plane as plane E, okay, because that is where the pressure is being exerted. Okay. So, you can also rewrite this as 0 is rho A1 V1 squared minus rho A2 V2 squared plus P1 minus PE. Okay. Sorry, there are two negative signs. So, let us remove one, okay, plus P1 minus I am sorry, there are two negative signs, that is okay, plus P1 minus PE, okay, times A1 plus or minus or we can even write plus PE minus P2 times A2 and then minus F tangential, which is neglected in our approximation. So, now we have to know what is the difference between PE and P1, okay, because PE is the pressure at the expansion, whereas P1 is the pressure at the upstream of the expansion where the fluid is flowing with some uniform velocity. Okay. Now, the pressure between point 1 and point E differs because of the fact that fluid is flowing in this short segment, but by choosing this station 1 sufficiently close to the expansion, we can assume that P1 will be very close to PE, because the only thing we are now neglecting is the viscous losses due to the flow in that short segment. So, we are going to assume that P1 is approximately PE. So, we have then by rewriting this equation P1 minus P2, okay, by rho is V2 squared times 1 minus A2 by A1. Okay. This is from the momentum balance. This is what the momentum balance gives us, the integral momentum balance, after making the assumption, two assumptions, that the shear stresses are 0 and the pressure at the sudden expansion is the same as the pressure at the upstream. Now, if you use the energy balance, integral energy balance, you will get that P2 by rho plus half V2 squared plus GZ2 is P1 by rho plus half V1 squared plus GZ1 minus viscous losses. There is no shear, there is no shaft work done because there are no shafts that are cutting across the control surface through this simple expansion. Now, one thing that we can say safely is that the elevations of the upstream and downstream are roughly the same. So, there is not much difference, potential difference due to gravity head. Now, then we have to substitute for P2 minus P1 from the momentum balance to get an expression for viscous loss. So, you have P2 by rho minus P1 by rho, which is obtained from the momentum balance. After substituting that here, we will get an expression for viscous loss, which is P1 minus P2 by rho plus half V1 square minus V2 square. Here I have not substituted P1 minus P2. So, instead of this P1 minus P2, we have to essentially substitute that. So, you will get the viscous loss L viscous, the viscous losses due to expansion as V2 square times 1 minus A2 by A1 plus half A2 by A1 whole square minus half. Okay. So, the viscous loss is equal to V2 squared by 2 A2 by A1 minus 1 whole square. So, this is the viscous loss that happens due to a sudden expansion. Of course, in reality this will not be exactly true because of the assumptions we make. So, we may have to do the measurement and then fit a constant with that, but the form of the dependence of the loss on the velocity is exactly like this. and the areas of the sudden contraction, but of course this relation will not be exactly true because of the fact that we have made this assumption that there are no shear stresses and the pressure at the expansion is exactly equal to the pressure upstream and so on. So, certain things are neglected in our analysis that makes our analysis approximate, but nonetheless what is powerful about the integral balances is that despite making such grossly simplifying assumptions, the functional form of the viscous dependence of the viscous laws on velocity and area is exactly the same as you obtain from this simplifying analysis, simple analysis, but it is just that the prefactor which turns out to be 1 in our analysis is not exactly 1, but it will be some number which can be fitted by using experimental data. So, this is one example of an application of integral energy balances where we have not just applied one balance, but we have applied a combination of mass, momentum and energy balance towards obtaining the viscous losses that are there in a sudden expansion. Okay. Now, another example of an application of the integral energy balance is to obtain the diameter of a free jet that exits from a tube. Okay. So, imagine you have a tube in which fluid is flowing under fully developed condition, let us say it is laminar for simplicity. Now, this fluid is exiting. Okay. Now, the moment it exits, it goes into the atmosphere and there are no shear stresses exerted by the surrounding atmosphere on the fluid, because the atmosphere is static and it is just air. So, the shear stresses exerted by the atmosphere on the fluid is negligible compared to the amount of shear stress the fluid faces when it flows through the wall, when it flows through the tube, a rigid tube with a rigid wall. So, in general the diameter of the tube d and the diameter of the jet dj that emerges sufficiently downstream from the exit of the tube, they are not the same. Okay. Because this is simply because of the lack of resistance to flow when the fluid exits into the atmosphere. So, what happens is it generally thins a little bit. The reason for that is because at constant flow rate, okay, the amount of volume that flows inside and outside is the same. So, we have V times D is V jet times D jet. Okay. So, this is from mass conservation. Okay. Since the fluid will accelerate, that is V will be less than V jet, okay, because of the fact that there is no resisting force here. Okay. The fluid will somewhat accelerate here, that means that D jet has to be so let us see. So, V in general, okay, so the diameter is in general different at the downstream because of the fact that there is no resisting shear forces here. Okay. So, V jet will be greater than V, therefore, D jet will be smaller than D, okay, to satisfy this mass conservation condition. So, D jet is in general smaller than D, and usually, as I have told you in several occasions before, that whenever you have a free jet, the velocity is uniform across the cross section of the jet. So, having said this, let us use the mass balance pi dj squared by 4 V1, sorry, pi d squared by 4 V1 is equal to pi dj squared by 4 V2. Let us call this station as 1 and this station as 2 in our analysis. Okay. Now, this is mass, integral mass balance applied between points 1 and 2, okay, of the CV. Okay. This is the mass balance. The energy balance, okay, becomes alpha 2 by 2 times the average velocity squared at 2 is alpha 1 by 2 the average velocity squared at 1 minus the viscous loss. Okay. Now, we have assumed that P 1 is approximately equals to P 2 and Z 1 is approximately equal to Z 2, because okay. So, now I am going to make a simple change in the CV, that my CV is right at the exit, the point 1, the plane is right at the exit of the tube. So, the velocity profile is just parabolic as it is just exiting the tube, but the pressure is approximately the atmospheric pressure. That is the assumption that we make, although it is not rigorously correct. This is an assumption that pressure as soon as it exits the tube is the same as the pressure far away in the free jet, which is the atmospheric pressure, but the velocity profile is still parabolic. So, if you do that, then alpha 2 is approximately 1 because the flow is uniform here, whereas alpha 1 is 2 because the flow is parabolic there. If I use these two relations, then I get a simple relation for, you cancel, let us say alpha 1 is, alpha 2 is 1. So, V 2 squared is simply 2 V 1 squared, that is one relation that we get, and therefore, if we substitute this in the continuity equation, we get d squared times V 1 is dj squared times V 2. So, if I square this equation, d squared times d to the 4 times V 1 squared is dj to the 4 times V 2 squared, but V 2 squared is simply 2 V 1 squared, dj to the 4 times 2 V 1 squared, V 1 cancels off. So, d jet is to the 4 is half d to the 4. So, d jet to the 4 is 1 by 2 to the power 1/4 times d, or d jet is 0.84 d. This is the equation that we get while using the integral energy balance between points 1 and 2, where the point 1 is just exiting the tube, okay, and the velocity profile is parabolic while the pressure is assumed to be atmospheric. Point 2 is sufficiently downstream the jet, where the jet velocity is uniform and the jet pressure is atmospheric. Now, the reason why the jet thins is because as soon as the jet exits the liquid, the liquid exits the tube, then it does not have any shear stress, so it accelerates a little bit. So, its velocity will be more than what it was at the tube, but continuity of mass implies that therefore, V 1 A 1 is V 2 A 2, therefore, the jet area will be smaller than the tube area, therefore, the jet diameter is smaller than the tube diameter, and it is small by a factor of 0.84. Now, we will stop here, and in the next lecture we will use the momentum balance, integral momentum balance, to solve the same problem, and we will see that the answers are not exactly the same. So, we will meet in the next lecture.